Well, thanks everybody for your patience this morning. I will dispense with the pleasantries and just ask us to give a very warm ShmooCon welcome to Travis Goodspeed.
Howdy, everybody. Just a quick show of hands. How many of you remember the old-timey shit like a Game Boy? All right, and how many of you remember this stuff called ROM, or read-only memory, back when it was read-only? Okay. So this photograph here is a mask ROM. And it is a photograph of a mask ROM that I made in my home laboratory. And if you zoom in on this photograph, you can see all of the ones and the zeros of the computer program. There are about 130,000 bits in here. About 96,000 of them are actually used, and at the very bottom of it, you can see that those dots are kind of missing. That's because there's a whole bunch of zeros at the end of the program. You can also notice that at the very far right of the image, some of the columns are darker than others. This is being clipped a little bit by the Windows machine, but the rightmost three columns are dark, and the one just to the left of them is very light. And if you flip that around, you get 1110, which is an E. And in ARM machine language, and I mean old-timey ARM, this is ARM 6, before they added the thumb instruction set. In the old-timey ARM instruction set, most instructions in a large program will begin with an E, because ARM has conditional execution. When you do an if statement, rather than have a branch in ARM, you also have the option of skipping individual instructions based upon the comparator results. And that E is visible from even this distance, which is how we figure out what those bits mean. There are tools for working with these. Today I'm presenting you a new tool for converting the photograph into the physically ordered bits. After that, it is a separate problem to convert those bits into logically ordered bytes. And that will only be loosely covered in this lecture, but is covered in other areas such as John McMaster's XOR-ROM project. All right, so to quickly review, Flash ROM and EEPROM are both, even though they have ROM in the name, they are writable. And they're electrically writable. And these are great for code that changes a lot. When you want to make an embedded system and you want to make 2 copies of your own homebrew game, Flash ROM is excellent for that. It's also excellent for storage on your cell phone. When you take a photograph, nobody else on Earth has that photograph, so there is no need to make it cheaply mass-producible. Mask ROM is the total opposite. It is programmed at the semiconductor design stage in one of the masks that forms the microchip. And making those masks is horrifically expensive. So that ROM will not be unique to that chip. Your minimum orders will be in hundreds of thousands, if not millions. And you will have nothing unique to an individual device. But this also makes it cheap for doing very high quantities of things that are absolutely identical, which is what we do in mass production. And because they're valuable there, it's a very good target for reverse engineering. These are used in smart cards in order to store the ROM that runs like the lower level operating system of the card. These are used in video games. If you're making a bajillion Mario cartridges, you might as well use a mask ROM rather than reprogrammable memory, because you're never going to reprogram that cartridge. The other great thing about these is that we can photograph them. We can chemically process the chip, understand what's inside of it, see the ones and the zeros, and then extract them. And this gives us a rather direct way to reverse engineer even very different targets. We don't need a software bug. We don't need a backdoor that allows us to read the memory. We don't even know how to talk to the chip, and we don't even need the chip to work. This works on broken chips. And that makes it great for getting the software out of these targets. Here's a photograph of one of the ROMs that we'll be covering today. If I zoom in a little, you can kind of see that there are these spots that are blue, and those blue spots indicate a bit. And if there's no blue spot, then there's no bit there. So what my software does is it converts that into marked bits. So wherever you see a blue or a red square, my software has identified that at that location there is a bit, and the red ones indicate ones and the blue ones indicate zeros. The little green one is me correcting a mistake in the software. Like any form of computer-aided drawing, you wind up with mistakes in your annotation, and it's very important to figure out how to effectively deal with those in order to get a clean or hopefully perfect image. Shit. Okay, everybody look at the left screen. There we go. So there are a couple of different tools for doing this sort of work. The first one to be published was ROM-par by Adam Laurie. And ROM-par allows you to mark a grid, and then within the grid it identifies all the bits. Bitracked by Chris Gerlinski works in a similar way. And my tool is a replacement for those two projects. There are also tools required for converting the physical bits into logical bytes, because the chip manufacturers are not putting these in the same order that you would write the bits with pen and paper, and we have to correct for that. ZOR-ROM by John McMaster is probably the best tool for this. It's a Python library that allows you to solve for a decoding if you can guess at what some of the bytes are. BitViewer by Chris Gerlinski is an interactive graphical tool that allows you to sort of mark up your beliefs about the chip and see what the bytes would be until they begin to make sense. All right, so let's dive into the chemical side of things and see how these chips are reverse engineered. The first thing you need is a big old jug of nitric acid. This is 65%, which is rather easy to acquire. It's a bit faster if you use red fuming nitric acid, but it has some disadvantages. Like it will detonate if you mix it with isopropyl alcohol, and that's bad. It also has this problem that it really loves to eat through bottle caps, including the black bottle cap that you see on this bottle. I don't think that this vendor sells red fuming nitric anymore. So we start with two chips. This technique works on through-hole chips, but through-hole chips have a lot more plastic on them. So you would really prefer to do this with the surface mount version of the chip if you have an option. I take my 65% nitric acid, I put a little bit of it over the chip in a beaker, and I heat the beaker. The green that you see here comes from the ground plane of the package, the little ground pad on the very bottom dissolving. The metal then buffers the reaction, and if you have too much metal, this will slow down or take forever to run. So if you're doing a through-hole chip or even a TSSOP with the legs coming out, you want to clip them off in order to have less metal to deal with. Boil it for a while, and then eventually I get the glass out. I drop the glass into acetone, and then I shake the acetone in an ultrasonic jewelry cleaner. This knocks all of the crud off, and then I can clean it again with isopropyl alcohol to get my bare dye. And the bare dye here is teeny tiny. Like, these things are very small, both for manufacturing and for yield reasons. You really want to be able to make as many of these from your wafer as possible, and you want any defect in the wafer to be contained within a single bad chip, so you try to keep your chips being as small as you can possibly design them to be. I then put that in my handy-dandy microscope, and on my handy-dandy microscope, I can see the surface of the chip. This is a metallurgical microscope, which means that the light comes down through the column and through the lens, and it also means that the lens needs to be ground in a way that the light will pass through it twice. A given photograph might look like this, and then I'll take many of them. I slide the chip and I get a second photograph and a third. And for large chips or high magnification, I need a lot of these photos. It's not uncommon for me to take more than 100 of either a chip itself or the ROM that I'm trying to extract. After I have them, there's this trick of aligning them. If you think of the one chip followed by its successors, right, or the one photo followed by its successors, they kind of overlap a bit. So the first one is followed by the second one, which is followed by the third one. And then I can stitch all three of those together in order to get a large panorama photo in which all of the details are clear and crisp. The software for doing this is called Hugin. It and a few scripts make it rather painless as long as I do not have a target that is photographically repeated. This is important because many of these system-on-chip devices will have multiple copies of the same organ. For example, we'll look at a cryptographic chip later that has a lookup table in order to do the cryptography. But it has one for encryption and a separate one for decryption of the same table in order to be able to perform both operations at the same time in full duplex. There is no way for the computer to know that a high-resolution photograph of the left copy of this organ is different from the right copy of this organ. And so those sometimes have to be manually marked up by overlapping features, which are these little colored dots that you see. And at the end of this, you get a complete image of the chip or of the ROM. The next trick that you need to do is called delayering. So that photograph was of the very top of the chip. Unfortunately, very few ROM images are visible from the very surface of the chip. Maybe 20% of them. And all of the rest, you need to delayer the chip and sometimes even stain the difference between P silicon and N silicon in order to get a working photo. The chemical for doing this is very dangerous. It's called hydrofluoric acid, and if you speak to any professional chemist, they will tell you to stay the hell away from it. You can also buy this at Lowe's as a rust stain remover. I love living in America, by the way. In Europe, all of this stuff would be a lot more complicated. One of the complications of this totally safe over-the-counter rust stain remover is that it dissolves glass. So you can't use a glass beaker or the glass itself will dissolve in the chemical acid. So you have to use a plastic beaker. And this being like the surface photo of another chip, if I zoom in on it, there are all of these little filler patterns that kind of hide what's in the background. And that's the sort of stuff that I'm trying to get rid of. I'm trying to get rid of the top few metal layers. I'm trying to get rid of everything that obscures vertically the piece of the chip that I want to photograph. So this being the surface of the chip, if I run it through one bath of hydrofluoric acid, most of that top is gone, and if I do a second bath, it's now completely gone, and I can see details of the chip that were previously hidden. And this is at low magnification. When you're very close in on the chip, it hides a lot more. In particular, if you have a transistor and the metal that connects the transistor is above the transistor, which is how chips are normally laid out, then the metal will also cover the piece of the transistor that tells you whether or not it works. And a mask ROM is very often built in what's called the diffusion layer by either putting in the little piece that makes a functioning transistor or leaving it out. And all of the broken transistors are zeros and all of the working transistors are ones. But the metal covers it, and that's why we need to do this delayering operation. So when we do the extraction, prior tools had this concept of a grid. And the grid was built up because the CAD software that designs these ROMs, in many of the ROMs, will place everything on a perfect grid, except that some of the columns are unused. And then your sampling software can then pre-process the image. It can maybe do edge extraction or color conversion. I do mine a little differently. My operator, the human operator running the program, we'll draw row and column lines. And wherever the lines intersect, that is a bit position. And the lines themselves can be freely moved or deleted or edited. So if your pictures are imperfect, if there's a bit more of a gap than there should be, if there's just a little bit of stretching or tearing, my software is pretty resilient to that. The tool will also help out with making sure that this work was done correctly. So in my tool, I specify a color threshold that tells me the difference between a 1 and a 0, because the 1s are darker. So I have design rule checks that look for things that are too close to the threshold. As in, if I say that anything with a green value of more than 127 is a 1, well, anything that's at like 128 or 129 is probably too close to that to be trustworthy. So the software can warn me of that, and I can go to that part of the photograph and correct that part of the photograph, maybe by moving the line a little, or maybe by looking at it myself and saying, software, I know that you think this is a 1, but I can visually see that this is a 0 with some dirt on it, so I'm going to force it to being a 0. The software also takes care of importing bits from other projects. So if I have 130,000 bits and I need them all to be accurate, and I have like a 0.01 error rate, that's still pretty high, but I won't have the errors in the same bit positions. So I can take 3 chips and I can do the chemical processing on all 3, I can photograph all 3, and then I can combine those 3 photographs not by merging them photographically, but by annotating all of the bits in each of them, loading up a project, and then asking which ones are different, and adjusting them until they all agree. So here is the first chip that we're going to reverse engineer. I was inspired to buy these by Ken Sharif, who does a lot of microchip reverse engineering. This is a greeting card microchip from 1988. And this would also be used in like cheap doorbells. And the idea is that this chip only has 3 pins. You give it power and ground, and then it gives you a pre-recorded melody. In the case of this image, it is Feuerlies by Beethoven. And if you look closely at this projector, you can see all of the 1s and the 0s on the right side of the chip. And you could even take a photograph with your cell phone and then reverse engineer it from the cell phone photograph. We're going to zoom in a little bit. Here are some of the bits. And you can see that there's this grid of like green lines. And then wherever they cross, there's either like a square with 2 blobs on the side, or there's a rectangle without blobs. And the squares with the blobs are the 1s. So what we can do is, in my CAD tool, I draw a line. I draw first horizontal rows through all of the bits, and then I do the same for columns. So if you look at these crossings, at each crossing point, you in your own head should either say there's a blob there or there's no blob there. As we go down from the top, we have 0, 0, 1, 1. And the software can then identify those bit positions. And it can do this for all of the bits within the ROM. We're telling it where the rows and the columns are. It's telling us where the bits are. We then call up this little dialog, which gives us a histogram of the bits. And in this histogram, we see that blue does not have a very big gap between our 1s and our 0s. There's just 1 mountaintop in blue. In green, we see 2 mountaintops with a little gap between them. And in red, we see 2 mountains with a very big gap between them. This tells us that green is not the color that we want to interpret. And blue is definitely not the color that we want to interpret. It's probably red. So first setting the threshold in green, I'm now saying that green is my difference. If it is darker than 91, it is a 1, and if it is brighter than 91, it is a 0. But if you look at this arrow, we see a red dot where there should be a blue one. It has misidentified this bit. And if you look around a bit, it does this a lot. And the reason is that the green color channel is not a great way to separate these things. So if we then move to the red color channel, we see that all three of those bits are now correct. The zeros become blue and the reds become 1. Yes? Yes, so as I have my dialog box open, I set the threshold by dragging a slider. And as I drag the slider live, I see all of the bits readjust themselves. And so visually, I will pick out a couple of bits that I know need to be zeros. And as I slide it, I wait for them to flip over. Or I'll do the same for ones. And doing this visually, I can get a pretty good check for the majority of the bits. Where this will go wrong is where a bit of dust comes in, or maybe my chip is damaged. I'm not doing the chemistry in a clean room. I'm doing it in what used to be my upstairs kitchen. And so the dust gets around. Not everything is perfectly clean. So I also need the software to help me out with design rule checks. So this is where it goes through, and it tells me that there is a problem whenever a bit is too close to the threshold and has not been forced. Forcing is where I use a key combination to tell the software, look, I know you believe this is a 1, but I'm a person and my opinion matters more. It's actually a 0. Or I can tell it like, hey, you think this is a 1. You're telling me that it's too close to the threshold. I'm telling you that you got it right and you don't have to worry about it anymore. It also looks for inconsistent row count. So I have all of these bits, and they're in columns and rows, and I wrote this algorithm that kind of sorts them by their X order and then their Y order and figures out how they line up. If that algorithm ever goes wrong, then the number of columns in a given row will be different from the other rows. And so we can highlight that as an error to tell me that either I made a mistake there or the algorithm got confused there. It also looks for overlapping bits. If I place the same, I'm placing a lot of these lines, and I'm kind of doing it on autopilot. My crosshair tilts to show me where it's going, and I'm just moving my mouse down, and I'm tapping the spacebar in order to mark these things. As I do that, if I hit the spacebar twice instead of once, I will have 2 rows in exactly the same position, which means that I will have 2 rows with exactly the same bit positions, which visually I will not notice, but the software will recognize that for me and warn me about it. Here is the design rule check feature where the software warns me about the bit errors. So here it's telling me that this particular bit is ambiguous, meaning that it's very close to the threshold. And we can see here that even though the rest of the bits in this photograph are identified correctly, that one bit is mistakenly a 0 even though it should be a 1. And for each of these bits, the display will then bounce to the local position so that I know which one the software is talking about, even though I have 130,000 or something to choose through. Yes? Great question. So the question is, am I looking at that exact position, or am I averaging for a region? By use of class inheritance in C++, I can change the behavior later. So I began a lot of this with the fastest thing to implement, and then I filled in the pieces that gave me trouble. Like my alignment algorithm was initially very slow. I had a project that you'll see later that was taking half an hour to compile by alignment to extract the bits. And so I rewrote that algorithm in order to make it fast. In the same way, at some point I will probably move to a strategy of, if not averaging a lot of pixels, at least taking like a group of 4 or something. Until then, I've found that doing a single location has been pretty good for accuracy. I'm not finding that I need to pre-process the image or that I need to add the OpenCV library or something expensive like that. I've found that just looking at the pixel position, grabbing the red-green-blue triplet, and then picking the threshold there has been rather accurate. One trick that I do though, is that I have infinite resolution. All of the coordinates that I use in the software entirely and without exception are floating point rather than integer. So my lines can have an angle that is sharper than the pixels would allow. This allows me to very carefully choose where the given values are sampled, and this also allows me to see that very often I'll see like errors in a row, and then I know that the row line position is the problem rather than the individual bit values or positions. And as I correct these, my design rule check violations go away, and then eventually I have no violations within the project. I also support exporting this in a number of formats. So I can take this thing and I can convert it to ASCII art, which is sort of the standard protocol for sharing mask ROM data. Going back 20 years, you would have a text file with just 1 and 0 letters along the row and matching the physical layout, and then you would write a script that would convert it. I also support comma-separated value because I often work with students, and students have this weird thing where people are poisoning their minds and telling them to use MATLAB. And comma-separated value is very easy to import into MATLAB. You can also do like JSON if you wanted to like graph out the bit positions or do a poster or something. You can do a Python array, and you can do like a high-resolution screenshot, even though you could never have that much resolution on your screen with all of the objects rendered in the right positions. I've also begun supporting a couple of different ROMs that I'm working with. Mark IV is a 4-bit architecture by Atmel that was in Adam Laurie's initial publication of his ROMPAR tool. And because that's like an easy chip to get started with and does not require delayering, I added support for it so that you can begin playing with this at home without dealing with the chemicals that will rot your bones. Only the ones that will burn your skin. I also support an ARM6 chip that I'll show you later. Writing these decoders is never hard after you know the ordering of the bits, but it is frighteningly frustrating before you know the ordering of the bits. John McMaster has been trying to solve this problem with his ZORROM tool, in that he has a solver where you can tell the tool that you have these bits extracted from, say, my tool. You've got the bits, and you think that the first byte is C0 and the second byte is 00, and then it will run through and try every different way of flipping the image and of rotating the image and of decoding it in different ways and trying to find an ordering that makes sense for the data that you provided. This works for about half of chips, and it's possible that with a bit more work it could handle a lot more than that. The ASCII output looks like this. Again, if you have these bits, you should be able to play For Release by Beethoven in like a shitty synthesizer style. All of this is photographic, so all of the data is available within the photographs. Here we have the ROM from a Game Boy. All of the bits were marked on here in a matter of minutes, and every one of those bits was accurate when I decoded it. The MD5 hash is exactly the same as the hashes from when others have extracted the same ROM. A couple of design tricks. The rows and the columns are just lines within Qt's graphics framework. The bits are just rectangles, and this allows me to use all of Qt's performance advantages. Like, I can switch this over to rendering in OpenGL by changing very little code. The rendering is also very fast. Even though I have a very high-resolution screen, even though I'm sliding around this thing, I very often hit pauses or have it slow down on me. My alignment algorithm is that I take all of the bits and I sort them by their x-coordinate. And when you do that, you get the very leftmost column, you just get those bits out of order. And for any given row, you should see the first one before the second one and so on. So by sorting them in this order and running through it quickly, I'm able to make this align the project in milliseconds rather than in minutes. And that allows me to very quickly run my test cases, export to files, without interrupting the operator or having to put like a please wait for me dialog up. And the speed of the operator and reducing the frustration of the operator allows you to get these bits out a lot faster and with a lot less hassle. And the most important decision I made was that from the very beginning, I supported both a GUI and a command line interface, which means that I have a makefile with test cases for every one of my projects. And as I change things about the project, I know that they continue to work. This allows me to run all of the design rule checks. This allows me to do all of the importing and the exporting and the comparison. Everything that you can do from the GUI, you can also do from the command line. I'm going to show you two last chips in my remaining minutes. This here is the MYK78, which is the Clipper chip. In the 1990s, the Clinton administration decided that they were going to be cool and they were going to allow us to have cryptography, but they wanted a government backdoor in it. Matt Blaze did a ton of work with this back in the day. He found out that a successor to the Clipper chip, called the Capstone, that we'll talk about in a minute, had a cryptographic problem that allowed you to fake being a part of the key escrow network while not actually revealing your key escrow packet to the authorities. This is the Clipper chip. If we zoom in a little, there are these two organs in the bottom left. These are ROMs. If we zoom in on one of them, we can see the bits. It's got like a little wiggly thing, and there's either a dark spot on the top or on the bottom of each row. Those are our bits. And we can mark them and we can extract them. And when the Clipper chip came out in 1993, it used an algorithm called skipjack that was not declassified until 1998. So nobody knew how this algorithm worked or how to be compatible with it or how to re-implement it. It has since been published, and this is a great situation because we can see what was secret compared against what 5 years later was no longer a secret with full documentation. And if you take these bits and you shuffle them in the right order, you will find that they are the F table from skipjack that was classified at the time of the chip's distribution. So it was possible to learn what later was revealed, but at the time was secret, by reverse engineering this chip. Another valuable thing to have is something called the family key. In the Clipper chip key escrow style, if I make a call to, say, my buddy Ozzy there, and I say, hey Ozzy, let's do a secret phone call. I hit the button, and that means that my device is responsible for giving our session key to the authorities. We do our little key sharing dance. We then have a session key. And I encrypt that session key with my own device key that the authorities have a copy of. So the government can decrypt it, but Ozzy can't. None of the rest of you can. But Ozzy needs to know that I gave our key to the authorities. So I wrap all of this up in the family key, which was not published, but which Ozzy's device can decrypt. And by doing that, he can then look at a hash of our session key and know that my device is snitching on us. Now, snitches get stitches, so let's see how this works under the hood. This is the Forteza card, which contained the successor to the Clipper chip. It's sometimes called the Capstone chip, although there might have been two. This is the MYK82. We then look at the die of it. The die is pretty cool. It's a lot bigger. It's a finer process. On the top right, we have an ARM6 CPU, which was very sophisticated for the time. You know, this CPU only came out in 1992. On the left, we have the main ROM, and at the top, we have lookup tables that contain the same skipjack tables that we saw on the Clipper chip. If we zoom in on the main ROM, we see bits. You've got the top ones, you've got the bottom ones. They're darker than the others. And if we zoom out, we see a whole bunch of bits. And if I go to the far right, you will see that on the far right side, the rightmost column is entirely dark, and the column to its left, the right side is dark, and the left side is bright. Imagine that backward, so the very most significant bits are on the right. That is 1, 1, 1, 0, which is an E, which is what most ARM6 instructions begin with, because that means that the instruction is unconditionally executed. So knowing that, we can then look backward. We can figure out that all of the words are written right to left. We can write them down, and then we can figure out their order based upon whether, like, when the output of one operation is consumed as the input of the next operation. It turns out that in the same way that the bits are written with right to left, the words are also written right to left. So on any given row, the rightmost bit is the first word, and then after that, the second. This allows us to decode the program, so we get all the 32-bit words out. Here in my code, you see the words for row 0 and then row 1, and it goes all the way down for 130,000 of these things. This is the C++ code that decodes it. This is binwalk telling us that it's definitely ARM instructions, meaning that we did some stuff right. And then we load it up in IDA Pro, and we can reverse engineer an NSA design from the early 90s just by photographing it. If you would like this tool, the tool is available for free on GitHub. It will redirect you if you go to maskromtool.com. And that's my lecture, and I hope you enjoyed it. Thank you. I'm looking for advice here. Do we have time for a question, or are we done? We have time for 2 questions. Yes? Oh, great question. So the question is, as I'm delayering a chip, how do I know how far I've gone in order to stop the reaction and stop the chip at the right point? So there is a fancy science way to do this, which is that you preheat the acid to a known temperature, and then with the acid at the known temperature, the amount of time should create the same etching on a given chip. The complications here are that different chips that I work with are from very different generations. And being from different generations, they have different thicknesses. So at the end of the day, what I do is I put 5 chips into the acid, and I take one out every 10 minutes. Or I start the acid and I add a new chip every 10 minutes. And then when I get the chips out at the end, I can sort them by how far it's burned down in order to find the chip that is at the best level. It's also a lot more forgiving than I ever expected. Very often, I will just throw the chip in for half an hour and find out that I'm seeing the right layer. This will, of course, become harder as technologies improve, and this technology does not work very well when the bits are smaller than the wavelength of light. And I'm done. Thank you kindly, everybody. I'll be around the conference, and see you there.